Now, with these parameters, it's easy for us to calculate either the y, which is the distance of any specific number of the fringe, or you can measure the wavelength, either take the constructive interference fringes, or you can take the destructive interference fringes. So if we know the distance between the double slits and the screen, and if you know the distance between the slits, and if you know the distance at which the particular fringe you are measuring, which we call it as y, and we can easily calculate the wavelength. Or if you know the wavelength, you can calculate the distance between the slits. Here is a table which shows you the lambda, which is the wavelength. If we want, we can actually use a different wavelength laser. For example, we can use a diode laser, we can use a Heine laser, and so on and so forth. So because this wavelength is dependent upon the various parameters which we have shown, so we can actually calculate the lambda, or in this particular case, we have shown how to calculate the d, the distance between them. Here, the n is the number of the fringe, which is the 5th, 6th, 7th, 8th, whatever it is, and L is the distance between the plate and the screen, and lambda, of course, is the wavelength, and y is the distance of that nth fringe. So it's easy for us to calculate, and this experiment is fairly easy. We can perform it in the lab. Now we'll talk about the diffraction. This is being given in page 37 of your text, and we will be showing presently the diffraction experimental setup also. Here we simply use the laser and let it go through the diffraction grating of a specific grating constant. We'll cast the diffraction orders on the screen, and we can actually measure the distance between same two orders. Let's say the distance between two first orders or difference between the second two orders. We can do that one, and then once again using the wavelength of the laser, you can either calculate the grating constant or you can calculate the wavelength of the light. Here is actual picture of the diffraction phenomena, which you can actually see the picture. This is how it looks like. First of all, this is coming through a diffraction grating where we have got the vertical slits. What we will be seeing, they look like circle because the laser beam itself has got a circular cross section. And here is a simple equation where is m is the order of the diffraction, lambda is the wavelength, b is the grating constant, and theta or sine theta is the angular dispersion. Well, if you know the distance between the y and the L, you can, for small angle approximation, you can write tan theta equals to sine theta equals to theta itself. This is the experimental setup. Here is the diode laser, here is the grating, and we can cast the orders on the screen, and then we can make the measurement between the two orders. That will be 2y, and half of that will be y. I can have a nice table in which we can write the grating constant, and then we can give the orders. This is 2y, the distance between the same orders on either side of 0, and then you can get 1y, which is the divided this by 2, and you can use the calculate the wavelength using this equation. As I said, if you know the wavelength, you can calculate the grating constant, or if you know the grating constant, you can calculate the wavelength, whichever you want. And you can actually find out the difference between the two wavelengths we have got. I hope you have enjoyed this explanation. Now we will be showing you the actual experimental setup itself.